material to review. And now we'll do screen share. Share. Okay, let's get this going. Let's get that. Okay, let me get started with some review from where we were. There's a lot of calculations here. So the last lecture mainly concerned Hartree-Fock theory, which is a variational approach to a multi-electron system, in this case an atom, in which the trial wave function is a completely anti-symmetrized tensor product of distribution of orbitals amongst electrons. In this case, they're electrons. You could do the same. You can use Hartree-Fock theory for other systems of identical particles like neutrons and protons in a nucleus. But in any case, the electrons is what we're doing. And so in any case, the Hartree-Fock trial wave function, which I call capital phi here, is given by a Slater determinant. The determinant permutes a collection of orbitals amongst a collection of electrons. The root n factorial here is a normalization. This can also be written as a normalization factor times the anti-symmetrizing projector times the Hartree, where the H subscript is Hartree, a trial wave function, which is just the unsymmetrized product of orbitals amongst the electrons. And as I say here, A is the anti-symmetrizing projector. The individual orbitals are assumed to be a product of a spatial part times the spin part. The spin part is just plus and minus a half that you assign at the beginning of the calculation. And the spatial part is determined by a spatial wave function I'll call U sub lambda of R. And these are the variational parameters. The Hamiltonian is broken up into two parts. There's the one electron operators, which is kinetic energy and interaction with the nucleus. And then there's the two electron operators, which are the interactions among the electrons themselves. So it's H1 plus H2. What we did last time, what we succeeded in doing was going through all the machinery of the anti-symmetrization and so on to calculate the expectation value of the Hamiltonian, that is to say these two terms, with respect to this Slater determinant up here. And it turns into a sum of two terms like this. One of them is this sum here, which comes from the H1 terms, single particle terms. This is in fact is the same result we had in the simpler Hartree theory with no change. However, for the two particle operators, there's a difference. In fact, I lied to you slightly because this is not the final form we had at the end of the hour last time. Let me exit out for now, take it out for now. We didn't quite get that far. It's actually correct what I wrote down there, but we didn't get to it yet. So let me show you where we did get. We got to this point where we had the sum on lambda less than mu of the same sum j lambda mu minus k lambda mu. Now, the I lambdas, j lambdas, and k lambdas are integrals, which I have summarized here on an integral page. And so here they are. The I lambda integrals are the expectation values of the kinetic energy and interaction with the nucleus of the given orbital. And the j lambda mu are the so-called direct integrals, which are the mutual electrostatic energy of the electron clouds coming from orbitals lambda and mu. And I've talked about them at least two times already in previous lectures, so I won't go over that anymore. The k lambda news are new, and I'll get to them in just a moment. That's what we ended up deriving at the end of the hour last time. Actually, they aren't really new. These are examples of exchange integrals, and we saw these exchange integrals in the perturbation theory for the excited states of helium. That's where we saw them before. And in that context, the orbitals U lambda were hydrogen-like orbitals, whereas here they're the variational parameters of the Hartree-Fock method. But apart from that, it's the same integrals that we saw before. In any case, I'll say something about the k lambdas in a minute. But anyway, with that understanding, what we actually derived last time was this expression, sum over pairs lambda less than mu is the expectation value of the two electron operator. Now, let me say something about these these exchange integrals here. I have room here below this on this integral page. So let me write it down here. Well, I want to list for you the properties of k lambda mu. There's 4 properties I want to point out. The first one is that the exchange integrals k lambda mu are real. It's fairly easy to see that if you take this integral and you take its complex conjugate, and then you swap the dummy variables of integration r and r prime, you'll find that it goes into itself, showing that k lambda mu is real. The second property of note is that k lambda mu is not only real, they actually are positive. This actually takes some proving to do, and I won't prove it. There's references are cited in the notes. You can look in there if you want to see the actual proof. But I have given you a plausibility argument for this. And that argument is that in the places in which the denominator r minus r prime is small, the regions of the the double configuration space, 6-dimensional space that you're integrating over, the regions where the denominator is small are precisely the regions where the numerator is positive, real and positive. So it's plausible that this integral is dominated by those regions and therefore is positive. In fact, it can be rigorously proven that it is positive. This is actually important physically because the k lambda mu's play a role. They're actually the energies which determine the effective repulsion which electrons of the same spin feel, which tends to make them stay further apart and therefore lower the Coulomb energy. I've stated this matter in the past by saying that when the spin states are highly symmetric, the spatial part of the wave function becomes more antisymmetric, and this keeps the electrons apart from one another and lowers the Coulomb energy. In any case, the K integrals are the mechanism by which that happens, and it's necessary for them to be positive for that interpretation to be true. In fact, you see they enter here with a minus sign so that the positive K integrals is subtracting from the energy. By the way, just to mention something, the J lambda mu integrals we got already with the Hartree theory. So the fact that in the Hartree-Fock theory, there's this extra exchange integral which is subtracting means that our expectation values, our estimates of the ground state energy, are going to be lower with Hartree-Fock theory than they were with the Hartree theory. That's because it's a better set of variational principle, better trial wave function. It's fully antisymmetric and satisfies the requirements, physical requirements of the system. All right, the third property of the K integrals are that they're symmetric in the indices lambda and mu. It's K lambda mu is equal to K mu lambda. By the way, these Greek indices lambda and mu and so on are referring to orbitals. And that's easy enough to see. If you just swap lambda and mu in here, this first factor here, by the way, is a Kronecker delta. That's just kind of a long notation for it's a Kronecker delta. But in any case, this is obviously symmetric in lambda and mu. And the rest of it is too. If I swap lambda and mu and then swap the dummy variables of integration, the K goes into itself. So it goes into the original integral. So these are symmetric in these two indices. And then finally, the fourth property that I want to mention is that on the diagonal, when lambda is equal to mu, or you got K lambda lambda, the exchange integral is actually equal to the direct integral on the diagonal, the J lambda lambda. Now the diagonal elements, if we look at J first, the diagonal elements are related to the self energy of the electron cloud for orbital lambda. J lambda lambda is that. It's actually that times 2. And we don't expect on physical grounds that the electron to be affected by its own self energy. I mean, a free electron, for example, with no others around, doesn't feel a repulsion from its own electron cloud. There's nothing like that happens. So these diagonal elements where lambda is equal to mu are actually non-physical. But nevertheless, it just so happens that the J lambda elements and the K lambda elements are actually equal to one another. And what that means is that in this sum in which we've got the difference between the two, we could include the diagonal elements here if we wanted to, and it wouldn't make any difference because the J and the K terms will cancel out. Having done that, we then can include the terms where lambda is greater than mu, and that double counts, but it's legitimate to do, it's meaningful to do that. And the result is that this entire expression can be replaced by the expression up above that I X'd out in red, which is an unrestricted sum on lambda and mu divided by 2 to take care of the double counting of the J minus K, the direct minus exchange integrals. And this, in fact, is the most convenient form for the energy functional. All right. So if I were able to erase the red markings, I would do that, because now I've justified the formula I wrote down originally. That is the energy functional now. Now, as we know, the energy functional, we need to add Lagrange multiplier terms in order to enforce the constraints. And the constraints that we spoke of earlier were the requirement that the individual orbitals should be orthonormal to one another. Recall that in the Hartree theory, the orbitals are not orthonormal. But in the Hartree-Fock theory, there's no loss in generality in assuming they're orthonormal, so we can require that. If we did that, we'd need to add a Lagrange multiplier term that would look like this. We'd have the scalar product of orbital lambda with mu minus Kronecker delta lambda mu. That's the quantity we want to vanish. So we'll multiply it by Lagrange multiplier epsilon mu nu, and then sum on mu and nu, and then subtract this. If we subtract this from this energy functional, then we get an effective functional that takes into account the constraints. Now, if you do, it turns out that if you do that, if you go through this and work out the equations, everything works. It's actually correct. It gives you the right answers. However, there's a simpler procedure, which is easier and gives the same answers. And so I'm going to follow that one instead. And the simpler procedure is the following, is that instead of enforcing the orthonormality of the orbitals by means of this Lagrange multiplier term, let me X this one out, because I'm going to replace it by a Lagrange multiplier term, which all it does is enforce normalization, just like we had in Hartree theory. So this is the sum on lambda. We'll enter with a minus sign, Lagrange multiplier epsilon lambda, and we just have the normalization integral lambda scalar product with itself minus 1. This lambda scalar product is an integral I call n lambda on my integral page. That's the normalization integral, which if you look on the integral page, you can see here it is. It's just obviously just the normalization. That's what n stands for here. In any case, this gives us an alternative Lagrange multiplier term. So combining the expectation value of h, which is the energy part, with this Lagrange multiplier part, we get a functional that we can vary. We can look for the minimum of that functional, really the stationary points of the functional. Critical points they're called technically. My claim is that the results that come out of that will automatically be orthonormal. Since we're not enforcing that explicitly, we have to prove that it's orthonormal. That's an extra step we have to carry out, but it's worth it to do it. So we're going to work with a functional, which is this h phi up here minus this Lagrange multiplier term. All right, including the term which has been, unfortunately, has been X'd out here. So if you will, let's take this thing here and add to it the last line, or subtract to it the last line, and that's the functional. This plus this minus this, we'll work with that. All right. Now we need to do the variations. I spent some time, maybe more time than I should have, in the last lecture explaining how the variations work. And some of the variations here are actually exactly the same for the Hartree-Fock theory as they were for the Hartree theory. In particular, the very first term is the same as in the Hartree theory, and we did it already 2 nights ago. But anyway, I've got a summary page here of variations, so let me go over it again just as briefly as possible so that you'll understand what I'm doing. The functionals that we're dealing with are functionals of the U orbitals and their complex conjugates, which we treat as independent quantities. It turns out if you vary with respect to one, you get an equation that's equivalent to what you get with varying with respect to the other. Therefore, we're only going to vary with respect to the complex conjugated orbital, because that turns out to be the simplest. So we'll vary only the U lambda star. As far as this I lambda term is concerned, it's really the sum on the I lambdas. If you write the sum out explicitly and take the variation, then you get this thing which you see over here. This integral which I've got here is really the same thing as I lambda, except that U lambda star has been replaced by delta U lambda. I got that because we wanted to vary to the delta U lambda star, and that's just all I've done. The rest of it is the same. Now, this is only one term of the entire functional that we're going to vary. And when we vary all the terms in it, we're going to require that the whole thing be equal to 0 for all possible variations delta U lambda star of R. And doing that is going to be equivalent to stripping off the delta U lambda star of R, as well as stripping off the integral, as well as the lambda, the sum on lambda. And if we do this, we get the term which contributes to the final Hartree, or now in this case, Hartree-Fock equation, which is just what's left over. It's just this operator times the orbital. So as you see, it's kinetic energy minus potential energy of the nucleus acting on an orbital. This is going to be one of the terms. In fact, this was one of the terms in the Hartree equation. So in any case, this is a review of what we did with the sum on I lambda. Now then, to remind you of our functional has now, here this, I shouldn't have X'd this out. There's the J lambda term. It's 1/2 J lambda mu. Let's look at that. We actually did that one also in the Hartree theory. It was the same J. The slight difference, however, in the Hartree theory, we summed on only lambda not equal to mu. We left off the diagonal terms, and here we're including the diagonal terms. Except for that, this calculation is the same that I did the other night. So let me just remind you again how it goes. So what I've got here is I've written out the J integral, but I've varied the U stars. So the J integral, if I go to the integral page, well, let's see, not here, let me get the integral page. If I go to the integral page, here's the J, it's got a U star in that absolute value and another one there. So varying the U stars gives me two terms by kind of a chain rule. And writing them out explicitly, here's what we've got. We get the variation on the 1/2 the sum of the J's. Here's the first term and here's the second term. This came from the delta U from the first absolute value squared, and this delta U mu star came from the second. Now these two terms are actually equal to one another, as you find by swapping mu and nu and R prime, which are dummy variables here. So what I'm going to do in evaluating this is get out my red pen again, and I'm going to X this out. We're just going to remove this, and at the same time remove the 1/2, because since they're equal, they'll take care of each other. Now then, in order to get the contribution to the final equation of motion, we run through this and we get rid of the delta U lambda star. We get rid of the integral over R, because that's what this depends on. It's integral over R here. And we get rid of the sum on lambda. And if you do that, you see the arrows here. This gives us the contribution to the final equation. Here's what it is. The sum on mu still survives. The integral over R prime still survives. The U mu squared up here still survives. I put the U lambda of R over on the right. I swap the order of these two terms, and there's your Coulomb denominator. So that's what you get here. That's the result. This is the contribution to the now Hartree-Fock equation. And you can see there's a certain quantity here multiplied times U lambda of R. The variable of integration is R prime, and the U lambda of R doesn't depend on it, so I can take it out of the integral. That's why I can put the square brackets around this. And so if we write the quantity in the square brackets as it's a function of R, let's write it as VD of R. D stands for direct. Then it becomes something that looks like a potential times the orbital. And indeed, this is then it becomes a term in the Hartree-Fock equation. Now, this was the same thing in the Hartree calculation, except we excluded the diagonal term mu equals lambda. Now we're including it. So that's what we get here. In any case, this thing in the square bracket is called the direct potential. Now, I happen to have here somewhere here a page of summary that has potential. So let me show you that. Here is the direct potential, V direct of R, and here is the expression for it, just copied. The direct potential, I interpreted it for you previously more than once. This is the electrostatic potential at field point R, which is due to the electron clouds of all of the electrons. In the Hartree theory, we excluded electron lambda, but now we're including it. So it's actually the electric field of all the electrons, including the one that's being driven by the Hartree-Fock equation. So this is an unrestricted sum on mu, but this is just basically Coulomb's law giving you that potential. So R here is a field point, R prime is a source point that's being integrated over, and the U squared is the probability density multiplied times the charge, which is -1, gives you the charge density. There's another factor of -1 in converting from the electrostatic potential to the mechanical potential. That's why there's no minus sign in this equation. Anyway, this is VD, then is the direct potential. All right, so that comes from the analysis of the direct integrals in the functional. Now, what about the exchange integrals? Those are new. So let's look at the variational calculation for the exchange integrals. To begin with, let's look at the exchange integral itself. it's going to be summed for the term in the functional. But here's the exchange integral itself. It's a Kronecker delta in the spins, double integral r and r prime. And then we got a distribution of orbitals lambda mu, but vector positions r prime, and r in the reverse order. This reverse order is why it's called an exchange integral with the usual Coulomb denominator. Anyway, that's what the K is. So if we vary the U star, we're going to get one term coming from that U star and another term coming from that U star. There's two of them in a kind of a chain rule. And the actual calculation is given by the last paper that I have here, summary paper. Here's the actual calculation. If we want to vary that term in the functional, it actually enters with a minus sign, which I've suppressed here. This is just the variation of the term. You get, as I say, two contributions. There's a delta U lambda star and a delta U mu star here, like that. However, just as happened with the direct terms, the second term is the same as the first term, it's equal to the first term. So I can throw it away if I'm willing to also throw away the factor of a half. And then to get the contribution to the equation of motion, I want to take out the delta U lambda star there, which is a variable function of r. So I take out also the r integration. And I also take out the lambda sum because this is the lambda index there. And if we do this, then the contribution to the equation of motion is what you see here. The sum on mu remains, the Kronecker delta remains, the integral over r prime remains. The rest of it is the remainder of the integrand here, which I've rearranged a little bit. I put the u mu of r first, I put the u mu of r prime star here second, and I put the u lambda of r prime, which is in the middle there, I put it last. Just rearrange those terms, and here's our Coulomb denominator. So this looks kind of complicated, but let's simplify the notation by writing it this way. It's an integral over r prime of a quantity which plays the role of a kernel of an integral transform multiplied times the wave function u lambda of r prime here. Whereas this kernel, which is written Vex stands for exchange, and lambda is in here because it depends on lambda, is basically everything else you see in this integral. And if I go to my potentials page, so this Vx here is called an exchange potential. It's sometimes also called a non-local potential. Notice that it depends on two positions, r and r prime. And notice that the role that it plays here is really as a kernel of an integral transform of what's otherwise is it's really a linear operator acting on this u lambda here, but it's a kernel of the integral transform, which carries out that operator. People call it a non-local potential. And here's the formula for it. It's just everything else in that integral that's summed up. So it's got the Kronecker delta on the spins, and otherwise it's a sum over all the orbitals mu of this expression here. This expression here may look kind of complicated to you, but if I can write it in a form that makes it look a little more symmetrical. Let's write it in scalar product r u mu for the first wave function. For the complex conjugated wave function, let's write it as mu scalar product r prime, like so, divided by denominator r minus r prime. And if you like the appearance of this is perhaps looks a little more symmetrical than the expression in terms of wave functions. In any case, this is what's called the exchange potential. They also call it a non-local potential, a terminology I don't like, but that's what people in the business call it. All right. Exchange integrals and exchange potentials are universal in the theory of many-body fermion systems. You'll run into it in any formalism that deals with problems of this sort. And as I explained earlier, they're responsible for the effective repulsion which particles that identical fermions feel that keep them apart when they're in the same spin state. I'll say more about that later. Anyway, that's the physical significance of these exchange integrals. All right. Anyway, that's the calculation of the variational calculation in some maybe more detail than I should have gone into, except for finally the Lagrange multiplier term. This is pretty simple, and it's the same as in the Hartree-Fock theory, so I'll just skip that. And I'll just proceed to writing down what the Hartree-Fock equations of motion are. So let me get these things out of here. I think I want to keep the potential page and the rest of them I can put aside. So when we gather together all those various terms, here's what we're going to get for the Hartree-Fock equations. It's going to be this. It's going to be p squared over 2 minus z over r, excuse me, acting on orbital u lambda of r. Then we have the direct potential v direct of r times u lambda of r. And for the exchange potential, it enters with a minus sign. It's an integral over r prime of v exchange, which depends on lambda of r and r prime, times u lambda of r prime. It's an integral transform, you see, of the unknown wave function. That's an r prime there to make it clear. It's an integral transform of the wave function, and that's equal to the Lagrange multiplier epsilon lambda times u lambda of r. So we can see once again the appearance of a kind of a pseudo Schrodinger equation for the unknown orbitals. I call it a pseudo Schrodinger equation because it's really nonlinear, which in contrast to Hartree's equation has this extra term v here. Also, in contrast to Hartree's equation, the direct potential is the same for all the orbitals because we included the diagonal terms. As I've mentioned, that's canceled by the diagonal term over here. The exchange potential, however, still depends on the orbital in question because of the spins, the Kronecker delta involving the spins here. So the exchange potential for orbital lambda, this driving orbital lambda, actually comes only from other orbitals mu, which have the same spin. So in general, you'd have some mixture of spin up and spin down. So if u lambda is a spin up orbital, then it's only the v exchange for spin up that's going to, for other spin up orbitals that will contribute to the exchange integral. All right, now then. So these are equations. We need to understand them and need to interpret them and get some understanding about how they're solved. The first thing I want to do is to prove that the orbitals are actually orthonormal, because we didn't enforce that by Lagrange multipliers. The logic goes like this. The first thing to notice is that this exchange integral, although it nominally depends on the orbital lambda, it actually does so only through the spin of orbital lambda. So remember, the spin up and spin down are assigned to the different orbitals at the beginning of the calculation in some way. We just decide which ones are up and which ones are down and put in there. And so some are up and some are down. But in any case, the v depends on lambda only through the spin of orbital lambda. And so if you wanted to, I could replace this ms lambda here by simply plus or minus a half. And then this lambda that goes over here is also plus or minus a half. Or I can put let me just put a plus or minus sign there to indicate which of these two choices is in here. And if I do that, then in the Hartree-Fock equation, let me also take that lambda and just replace it by a plus or minus sign. And then we have effectively two coupled Schrodinger equations, one for spin up orbitals and the other one for spin down orbitals. We use the plus v if u lambda is spin up, and we use the minus v for if u lambda is spin down. Okay, there's no, that's just a reformulation of the equations. Now then, let's take two orbitals, lambda and lambda prime, and let's suppose they're not the same orbital. There's two cases. Let's suppose this ms lambda is equal to ms lambda prime. First of all, let's suppose although the orbitals themselves are different, let's suppose they're both of the same spin. Well, what that means is that the orbital u lambda then are solutions of the Schrodinger, one and the same Schrodinger equation. Because of the same spin, these are both use the same, either a plus or a minus in here. And therefore, being eigenfunctions, distinct eigenfunctions of the same single particle Hamiltonian, they are orthogonal to one another because the spatial wave functions are orthogonal. This is a purely spatial wave function. On the other hand, if ms lambda is not equal to ms lambda prime, then one's driven by the plus v exchange and the other's driven by the minus v exchange. So they're eigenfunctions of different single particle spatial parts anyway, single particle Hamiltonians. So the spatial parts are not orthogonal anymore. However, the spin part's orthogonal because of this condition. So either because of spatial or because of spin, the various states u lambda, or the various states lambda and lambda prime are indeed orthonormal to one another, and we have therefore shown that we get orthonormality of the single particle orbitals as claimed. All right. Now, the next topic then is, how do we solve these Hartree-Fock equations? They're more difficult than the Hartree equations, mainly because the exchange term involves an integral transform. However, the basic idea is the same as before. We do it by iteration. So let me again sketch you a flow chart. We start with a guess of the orbitals u lambda of r, which could come from a Thomas Fermi model as before. I mentioned that before. Once we know the u lambdas, we can calculate the direct potential Vd of r and the exchange potential V exchange of r and r prime, like that, for both types of spins, plus and minus. And then we can plug them in here. We get these two Schrodinger equations. And then we solve. I'll leave some space in here because I want some space to add some things. And then what we do is we solve those Schrodinger equations for the orbitals. That's to say, for the eigenfunctions of both spin up and spin down of the spin up and spin down effective or pseudo Schrodinger equations. Now then we take those orbitals and we compare them to the old orbitals we started with and ask if we've converged yet. Question mark. And if the answer is no, we go back and we do this again, we iterate. And if the answer is yes, we're done. Okay, that's basically the same flow chart that we used in the Hartree theory. Now, in the Hartree theory, as I pointed out, it was pointed out by Hartree actually. The work is simplified tremendously if we can work with central force Hamiltonians instead of with fully three-dimensional ones. These direct and exchange potentials are not rotationally invariant in general. Look at the direct potential; it's just the sum of these things here integrated over r. And there's no reason why it should be rotationally invariant. Actually, later on, you may see that, I'll tell you about this, if you have complete subshells, it turns out they are rotationally invariant, but otherwise they're not. So this is a lumpy potential and is not rotationally invariant. Therefore, you can't separate the Schrodinger equation in spherical coordinates. So it's much harder to solve. So as Hartree did, what we suggest is that first of all, we replace the V direct of R vector with what I'll call V over bar direct of R scalar. That's the one substitution we make, where the definition is this: V direct over bar of R scalar is the integral over solid angles of V direct without an overbar R vector. In other words, we just take the potential and average over solid angles. That gets rid of all the lumpiness in it and leaves us a rotationally invariant potential. And let's use that there. Let's make that change, do that averaging. Likewise, let's take the V exchange plus and minus of R and R prime. That's the kernel of the operator, what's called the non-local potential. And what we'll do is we'll average this over rotations to produce what I'll call V exchange bar plus and minus of R and R prime. And I'm going to omit the details of how one averages over rotations, except to say that it involves averaging over the rotation group. One basically integrates over all the Euler angles. And the result is that you get a V exchange over bar plus or minus as an operator, which commutes with rotations. It means U of R dagger is equal to the V over bar plus and minus exchange. I'm going to omit the details of how one does this averaging here. I give you an explicit formula for the direct potential, but for the exchange potential, I'm going to omit it because it's too technical, I think, for what I want to do with this course. But the idea is you average over the group, the rotation group, and you get something which is rotationally invariant. It's still an integral transform, but now it's rotationally invariant. The operator, which is represented by the integral transform, is rotationally invariant. And so that makes the potentials both up and down, direct and exchange, rotationally invariant. And now I'll do one final approximation, which is to take the V bar plus and minus and just replace it by V bar exchange, which is equal to 1/2 of V bar exchange plus V bar exchange minus. As I say, we'll average over the spin as well. And we do that because it makes it invariant under spin rotations. And so the result is we obtain now, if we use these rotationally averaged potentials over both orbital and spin rotations, is we end up with a single particle operator driving our orbitals, which is overall rotationally invariant for both orbital and spin. And that makes solving for the U lambda var much easier. Of course, it's an additional approximation, but because atoms tend to organize themselves into roughly spherical shapes, we hope this is not too bad an approximation. To be more careful about this, atoms do that in the ground state or in states that are close to the ground state. If one were dealing with a highly excited state of the atom in which all the electrons were blasted all over creation and maybe in high quantum numbers, then it wouldn't be a good approximation to say that it's nearly spherically symmetric. But that's less common in practice. One is interested in those things less often, and if you had that, you'd have to use different techniques. In any case, this then becomes a modified procedure for solving the equations. Now, if we use this procedure for solving the equations, then the single particle Hamiltonians which result, in fact, let me write this out as a single particle Hamiltonian. I'll use a lowercase h for it. What is it? It's p squared over 2 minus z over r plus v direct average, which is a function of r, it's a central force potential, minus v average exchange, which has been averaged over spin as well. And I won't try to write out any dependence on this. I'll just write this as a symbolic notation for the operator, which we understand is implemented by means of an integral transform. But it's a linear operator, it's Hermitian, and it commutes with rotations. So this is our single particle Hamiltonian. And now all the orbitals then, all the orbitals are eigenfunctions of that Hamiltonian with eigenvalues epsilon lambda, u lambda of r. Okay. Now, since these are now all rotationally invariant, it follows that the lambdas, which are the labels of the single particle orbitals, are actually central force quantum numbers. That is to say, this is a collection of n, l, m sub l, and m sub s quantum numbers for this system, because it's now a central force problem. And so the labels of the orbitals now can be replaced by central force orbitals, central force quantum numbers.
I have one question.
Yes.
So how do we actually guess the spin part of the orbital at the first place? And are we updating also the spin part of the orbital, or only just updating this spatial part?
We started out by assigning spins, either spin up or spin down in an arbitrary way. We'll worry about that later, exactly how to assign the spins. But when you do that and you go through this procedure, the energy doesn't depend on the spin assignment anyway. It's a magnetic quantum number. We made things invariant under the spin rotations, you see, by doing this averaging here. And so if they're invariant under spin rotations, then the energies don't depend on the spin quantum numbers.
Okay, thank you.
Okay. In fact, that was my next point, is to say these are the quantum numbers of the orbitals, that i.e. the wave functions, single particle wave functions. However, the epsilon lambdas, which are the Lagrange multipliers, I'm calling them pseudo energies because they're the energy eigenvalues of the pseudo Schrodinger equation. These now are central force energies, and therefore they only depend on the N and L quantum numbers and not on the magnetic quantum numbers. So they can be written as epsilon sub NL, like that. All right. Now, an NL combination here, which occurs here, is called a subshell. That's the name for it. You'll see why if I just give you some examples. If we have, for example, 1s, this is n equals 1 and L equals 0. If I have 3p, this is n equals 3 and L equals 1. If I have, if I have 4f, this is n equals 4 and L equals 3, I think, L equals 3. So these are spectroscopic notations for subshells, and they stand for what I'll write as N and L in the general case. So what we have then is we've got the H's, the H's acting on the U, N, L, ML, and MS gives us an epsilon NL times U sub N, L, ML, and MS. This is kind of like what the single particle Hamiltonian looks like. Potentials, you have to remember, of course, that the potentials that are in here are determined self-consistently. Now, the energy estimate, the pseudo energies epsilon and L depend only on the quantum numbers N and L. The Hartree-Fock trial wave function, which I wrote in Ket language as a capital Phi, is specified by the collection of the lambdas, that is to say, of the orbitals, which in turn, as we now recognize, is a collection of the central field quantum numbers, like so. As to say, there's one such set of quantum numbers for each orbital. And moreover, the Slater determinant, or the Hartree-Fock trial wave function Phi, which is a Slater determinant, it doesn't depend on which electrons are assigned which orbitals, because all the orbitals are permuted amongst all the electrons. You can't say electron 1 is in some orbital. That makes no sense. They're all in all of them are in all the orbitals. What you can talk about is which orbitals appear. There's a certain set of orbitals which appear. Now there can't be any repetitions in those orbitals, because if there are, you've got two columns of the Slater determinant which are identical, and therefore the Slater determinant vanishes. This is the Pauli exclusion principle. It says the electrons that go into it all have to have different sets of quantum numbers. So they're all distinct sets of quantum numbers, the NL, ML, and MS quantum numbers. So what this is going to give us then is some set of subshells, N and L, and some set of magnetic quantum numbers that tell the how many elements in those subshells are occupied. For example, the 2p subshell has N equals 2 and L equals 1. The L equals 1 is the main point. Because of the L equals 1, there's 2 L plus 1 M sub L values, and there's 2 spin values, M sub S values, 2 spin values. So that gives you 2 times 3 equals 6. And therefore, in the 2p subshell has in effect 6 different slots, or 6 different possible electron states that can be put into that subshell. This is the occupancy or the capacity of that subshell. Likewise, the 1s subshell only has 2 slots, and the 2s only has 2 slots. Now, when we're carrying out this iteration to determine the ground state energy of the atom, when we solve for the U lambdas, we're solving a single particle wave equation. And of course, it has an infinite number of eigenvalues and eigenfunctions. But we need to choose only n of them to plug back in here to compute the self-consistent potentials. So presumably what we do here is we choose the ones that have the lowest energies and put in, because we're interested in the ground state. And so we converge on those. If there's any question about what's going to make the lowest energies, we make different trials, try different things, and converge for different choices until we find the one that gives us the minimum energy. When we've done that, when we've got this collection of orbitals that gives us the minimum energy, we obtain what is called an electron configuration. So let me explain that, which I'll explain. I think the easiest way to explain it is to give you examples. You probably have seen the terminology before, but here's what it means in the context of Hartree-Fock theory. For example, if I take the atom carbon and it has electron configuration that's written this way, is 1s squared, 2s squared, 2p squared. The occupancy of the 1s, 2s, and 2p orbitals are 2, 2, and 6, as I mentioned earlier. What this means is in the ground state of carbon, 2 electrons are in the 1s subshell, which means that it's filled. 2 more in the 2s subshell, which means that it's filled. And 2 more in the 2p subshell, which means it's only 1/3 filled. Only out of the 6 slots, only 2 of them are filled. In fact, what that means is that of the 6 slots that are in here, they differ by their magnetic quantum numbers, both orbital and spin. And these 2 electrons that are put in there, if I give the electron configuration, I don't say what those magnetic quantum numbers are. There's a choices for them. But the choices of the magnetic quantum numbers don't affect the energy. And that's why those quantum numbers are omitted in specifying the configuration, because the configuration is just telling you, it's giving you basic information about the ground state. So this in fact is the electron configuration for the ground state of carbon. Now, I want you to understand, this is probably not clear from elementary chem courses. This is, I'm sure, is not made clear, but the electron configuration is a characteristic of the ground state carbon that's based on an approximation. It's based on the approximation of, in the variational sense, of finding the multi-particle wave function that's composed of single particle orbitals properly antisymmetrized, which minimizes the energy. It does not mean that the real ground state of carbon is such a Slater determinant. It is not. That Slater determinant that minimizes the energy is just the best approximation within that family of trial wave functions to the actual ground state. The actual ground state can be written as a linear combination of Slater determinants because they form a basis in the antisymmetrized Hilbert space, the physical Hilbert space for the atom. But the actual ground state does not consist of a single such term, but rather there's many terms in it, which one can calculate with more sophisticated methods. So this is the best approximation to the ground state by means of a single Slater determinant. That's what the electron configuration means. All right.
So just to be clear, at this point, we don't have any way to know what, for example, the spins of the 2 electrons in the p orbital would be.
Yeah. So let's talk about you mean the assignment of the spin quantum numbers? Is that what you mean?
Yes.
Yeah. Okay. So let's talk about that. When we fill up the 1s orbital, which we do in carbon in order to get the ground state, we have to put one spin in, a spin up, and the other one a spin down, because they've got to be distinct orbitals. There's no choice in that. The same is true for the 2s squared shell, because it's filled. Subshells that are filled are said to be complete. So complete is the language that people use in this, but it just means filled, whereas incomplete means not filled. So carbon has 2 complete subshells that are filled and 1 incomplete subshell. So you're talking about the incomplete subshell, and you're saying that the magnetic quantum numbers are not specified. That's to say, we could make them anything that we wanted to, and we get the same energy. And within this scheme, the energy doesn't depend on the magnetic quantum numbers. The same thing is true for the M sub L quantum numbers. Energy doesn't depend on them either. So the magnetic quantum numbers, both ML and MS, there are certain choices of them inside this incomplete subshell. And hopefully tonight, I'll have time to get to it, we'll talk about how many choices there are and where they go. But you're quite right, the energies don't depend on them, and I haven't said what they are because I don't need to in order to talk about the ground state energy.
Okay, thank you.
Okay, I'll make one more point about that. The fact that there's more than one way of assigning those magnetic quantum numbers means that this ground state energy is degenerate in a certain sense. There's more than one Slater determinant that gives the same energy. We'll get back to that. In fact, it turns out it's 15-fold degenerate. 15. All right. All right. So this is the essence of one approach anyway to Hartree-Fock theory in multi-electron atoms. But once you've carried this out, like for example, if we carried it out for carbon, what would we find? Well, we find the wave functions. These are the U of R's, where the U lambda of R's. Well, the U lambda of R's, given that we now know that these are central force wave functions, they look like this: RNL of radius times a YL M sub L of theta and phi. This is, of course, is multiplied by the spin part to get the total wave function. But of course, we know what the YLMs are. So in determining the U lambda of R's by means of our iterative procedure, the main thing that we're getting is the radial wave function. So if you like the output of carrying out this numerical, it has to be done numerically, this numerical work on the carbon atom is going to be the following things. We'll get the radial wave function for the 3 subshells. There's the R1s of R, there's the R2s of R, and there's the R2p of R. Those 3 radial wave functions. We'll get the corresponding energies, epsilon 1s, epsilon 2s, and epsilon 2p. These are the pseudo energies, the pseudo eigenvalues of the Hartree-Fock equations. This is the information we get. In fact, we don't really need to say anything else. This is the minimum information needed to completely specify the problem, because once we know the wave functions, which these radial wave functions is all we need for that. I mean, these are determined numerically, and you'd have to tabulate them or something to pass it on to somebody. But it's only 3 functions and they're only of 1 variable. So we've got that, and then 3 numbers. So once we've got those wave functions, we can then compute the direct and exchange potentials from them, the formulas I gave you a moment ago. So the potentials become known. So the single particle Hamiltonian, of which these things are eigenfunctions, are now known also. So the potentials then are known as well once this information is given. All right. So let's suppose we've done a problem in which we've set up all of that. Now, does this give us an adequate description for the ground state of, let's say, carbon? And the answer is no, it doesn't. It doesn't even give us a qualitative description of what you see if you look at the spectrum of carbon for the low excited states. And the main reason is that these Slater determinants, which comprise the trial wave functions that we're working with, are not eigenfunctions of all of the good quantum numbers of the Hamiltonian we're trying to solve. Let me address that issue. I'll remind you the Hamiltonian we're trying to solve. I'll just write it out again. It's the sum on I equals 1 to n of the kinetic energy pi squared over 2 minus z over ri, the interaction with the nucleus. And then it's a plus the sum I less than j of 1 over rij. This is our electrostatic model, like this, and we call this H1 plus H2. Now, I pointed out earlier in last lecture that this Hamiltonian, it's only an approximate Hamiltonian, but it has certain exact conservation laws. Let me list them on this next page here. The operators in question are L squared and LZ, S squared and S sub Z, and parity pi. These are the main operators that we want. And the corresponding quantum numbers we'll call capital L, capital M sub L, capital S, capital M sub S, and just pi. We'll write pi both for the parity operator as well as its quantum number. So this is the list here. So we know that the exact eigenfunctions of H are exactly eigenstates of L squared LZ, S squared SZ, and pi with these quantum numbers. Now let's suppose we've determined our Slater determinants by our iterative method up above. Are they eigenfunctions of these 5 operators? The answer is no. They're only eigenfunctions of LZ, S sub Z, and pi, but not of L squared and S squared. Here's how we know this is true. The Hartree function, the Hartree wave function phi, as I've explained, is a normalization times the anti-symmetrizing projector multiplied under the Hartree-Fock trial wave function, where that's acting on the Hartree trial wave function on the right. And the Hartree trial wave function is just the simple product of orbitals over electrons, like so. Okay. Except now that we know these orbital labels here are actually N, L, M sub L, and M sub S quantum numbers. They're central field quantum numbers. All right. Let's look at LZ, the operator LZ. LZ is the sum over the atoms, I equals 1 to n, of L sub Z sub I, the Z component of the orbital angular momentum of particle of electron I. If we apply this operator LZ to the Hartree functional, and each one of them is an eigenfunction of LZ with quantum number M sub L, this is just going to bring out the sum on I equals 1 to n of M sub L sub I. It's just the sum of the MLI quantum numbers. Now the Hartree-Fock functional is the Hartree functional anti-symmetrized, in which all the orbitals are permuted amongst all the electrons. But permuting the M sub L sub i's is not going to change the sum. It's invariant in the permutation. So all n factorial terms that are contained in this Hartree-Fock functional all have the same eigenvalue. And therefore, what we can say is that this phi is actually an eigenfunction of LZ with an eigenvalue I'll call M sub L, capital M sub L phi. where capital M sub L, I'll write it this way, is now the sum, instead of writing the sum over electrons, I'll write it as the sum over orbitals, lambda equals 1 to n of lowercase m sub L sub lambda, meaning just the M sub L quantum numbers of all the orbitals. So I think that's pretty clear. And the same story applies to S sub Z for spin. S sub Z acting on phi is equal to M sub S times phi, where the M sub S quantum number is now the sum lambda equals 1 to n of M sub S sub lambda. Okay? So the grand quantum numbers for the whole atoms are just the sums of the magnetic quantum numbers for the individual orbitals. And in particular for the spins, it just counts the number of spin up and the minus number of spin downs that you made in your original assignment. All right. Parity also comes out. This is also an eigenstate of parity. And the reason is, again, if I apply parity to the Hartree trial wave function, each of these is a central force eigenfunction, and its parity is -1 to the L. So letting parity act on that brings out the products of the -1 to the L's. So I can write this as pi eigenvalue, let me write as an eigenvalue here, times phi, where the pi eigenvalue is equal to the product of lambda equals 1 to n of -1 to the L sub lambda. It's the product of the -1 to the L's for the various orbitals. Okay. Now here's some comments to make about this. These quantum numbers, overall quantum numbers, ML and MS for the entire atom, actually, although I'm summing here over all the orbitals, it's actually only necessary to sum over orbitals in incomplete subshells. Because in the case of complete subshells, the number of MLs positive and negative are equal and they cancel each other out. And the same thing's true for the spin quantum numbers. Plus and minus are all balanced out. So the sums are 0 for complete subshells. So these two sums, if you want, can be taken over incomplete subshells only, and it won't make any difference. So for example, in the case of carbon, it's going to be, the answers are going to depend only on those last 2 electrons in the incomplete subshell. As far as the parity is concerned, again, part of this product, which is taken over complete subshells, is always going to involve an even number of factors, because every subshell has an even number of slots, 2, 6, and so on. So those are just multiply out to give you 1. So again, this product again only needs to be taken over the incomplete subshells. However, in the incomplete subshells, the L is all the same. It's the same for all the factors. So what that means is the parity actually depends on the electron configuration only. It doesn't depend on the magnetic quantum numbers. So for example, carbon that has 1s squared, 2s squared, 2p squared. The parity of the full subshells is 1. The parity of the 2p squared, well, the p electrons are L equals 1. Each one gives you a parity of -1, but since there's 2 of them, you overall get pi is equal to +1. Whereas in nitrogen, which has 1s squared, 2s squared, 2p cubed, the parity is equal to -1 because there's 3p electrons and each has an odd parity. So you see the parity depends only on the electron configuration, whereas the LZ and S sub Z depend on the magnetic quantum numbers in the incomplete subshells. All right. So as I mentioned, this is one of the main drawbacks of the simple-minded Hartree-Fock iteration is that we get trial wave functions that are not eigenfunctions of all of the good quantum numbers. They are eigenfunctions, as I've just shown you, of LZ, S sub Z, and pi, but not of L squared and S squared. Why not? The reason is that L squared is really the sum on I of the Li vectors quantity squared. So it's got all kinds of cross terms in here. And when you let this act on a phi even on a Hartree state, much less a Hartree-Fock state where you're permuting things, it doesn't just turn into a sum that's invariant under the permutations of the orbitals. So these Hartree-Fock states are not eigenstates of L squared and S squared. All right. So what we'd like to do is to construct eigenstates that are eigenstates of the good quantum numbers of the system, because we know the energy levels that we actually observe are labeled by those good quantum numbers. All right, so how do we do that? Well, here's how we do this. We take the output of Hartree-Fock theory and we feed it into a kind of perturbation theory. Let me explain how this works. The Hartree-Fock trial wave function, which I'll again write as phi here. This is a Slater determinant, but I won't write it all out because we've seen it already. This Hartree-Fock trial wave function is actually the eigenfunction of a multi-particle, not a single particle, a multi-particle Hamiltonian I'll call H naught, with an eigenvalue E naught. And this H naught is not the original Hamiltonian. H naught, in fact, is this. It's the sum I equals 1 to n of the single particle Hamiltonians that drove the Hartree-Fock orbitals. Pi squared over 2 minus z over Ri plus the direct potential averaged as a function of Ri minus the exchange potential averaged, which is evaluated for particle I like this. This is an integral transform. In any case, it's a sum of single particle, it's a sum of single particle Hamiltonians, one for each electron. Whereas, of course, our original Hamiltonian had two terms, of which the second term had two electron operators in it. But this Hamiltonian, if you allow me to write it this way, this is a sum I equals 1 to n of H sub I. And the single particle orbitals are eigenfunctions of the H's. This came out of the Hartree-Fock theory, like so. So therefore, when I apply the sums of these H's to any one of the n factorial terms in this Slater determinant, I'm just going to get a sum of the epsilons, and the permutation of that sum is not, the permutation won't affect the sum. So it's the same value for all of the terms of the permutation, and so therefore it gives us the same answer. And what that means is the E0, which appears here, is just the sums of the epsilons. So E0 is equal to the sum on lambda of the epsilon lambdas. Now I can also write this in the following way as a sum on subshells in L of an integer I'll call nu sub NL times epsilon NL, where nu sub NL is the occupancy of subshell NL, of subshell NL. So this is just saying that since the energies are independent of the magnetic quantum numbers, you just multiply by the occupancy and add them up and you get the total energy. It's the same thing as this sum. All right, in any case, this just confirms what I was explaining a minute ago, that the result of the Hartree-Fock theory, phi, that Slater determined that we get out of it, actually is an eigenfunction of a certain Hamiltonian H0, and here it is. This is not the same as the original Hamiltonian. It's not the same as the electrostatic model that we started with in trying to solve. But to say it again, our Hartree-Fock result is an eigenfunction of this H naught. Now, this raises the possibility of doing perturbation theory. We do it in the following way. We write a Hamiltonian, we'll write as H is equal to H0 plus H1. These aren't the same H0 and H1 as before. The H0 is the same H0 you see up here. And as far as the H1, here's what it is. It's the sum on I less than J of 1 over Rij, which of course is the inter electron Coulomb interaction, plus the term, let me write it this way, is minus the term, the sum I equals 1 to n of V direct of R averaged minus V exchange. This is some Ri minus V exchange bar comma I, like this, like so. And you see that if I define H1 in this manner, then H0 plus H1, look what we've got. On H0, we've got the two terms, kinetic energy and interaction with the nucleus, plus direct minus exchange. Here we've got the exact inter-electron Coulomb interaction minus direct minus exchange. So the direct and exchange terms have just been added and subtracted. And the result is this H0 plus H1 is actually equal to our H electrostatic model that we started with. That's the one we wanted to solve. Okay. So H0 plus H1 is now, it's written in a complicated way, but it's the problem we want to solve. Now here's some physical idea behind this. This direct minus exchange potentials is a sum of single electron operators determined by a somewhat complicated way. But they came from the 2 electron operators of the exact Hamiltonian, came from taking expectation values and minimizing. So in some sense, these 2 terms taken together represent a kind of an angle averaging, angle and spin averaging of the interaction of the electrons amongst themselves. And so taking this exact inner electron Coulomb energy and subtracting off in effect the angular average of it, what we get is a term which is sometimes called the residual Coulomb interaction. So the idea is that although this exact inner electron Coulomb interaction is too big to treat by perturbation theory, once we subtract this stuff, the average off, what's left over is small enough to treat by perturbation theory. And so we can get a successful perturbation theory and solve the original problem we really wanted to solve with this electrostatic model using this H0 plus this H1. So that's the strategy. And we'll see how far we can get it in the next 18 minutes or something that's left in the lecture tonight. Maybe before I go on, let me ask if there's any questions at this point, because there's a lot of steps of logic in this. Any questions? Okay, it's an interesting procedure.
So I have a question.
Yes.
When you're treating this as a potential, you're like, so VD and VX depend on R, right? But here you're like holding them fixed. You've already determined them and you're holding them fixed and treating them like a linear equation.
They depend on the orbitals. They were determined self-consistently, so we needed to iterate and find the orbitals that gave these potentials. However, once those potentials are determined, the orbitals are genuine eigenfunctions of this single H, right here, they're genuine eigenfunctions of this Hamiltonian. So in other words, once the orbitals are determined, then these potentials are determined, and therefore this H operator, single particle Hamiltonian, is determined as well. So now it's eigenfunctions. Not only the ones that went into making the potentials, but all the others as well. There's a complete set now, you see. They're all determined.
All right, thanks. Makes sense.
Okay. All right. Now, here's a question that arises. If this procedure is going to work, and we've diminished the size of the inner electron Coulomb interaction by subtracting off the rotational average, and this term therefore is small enough to treat by perturbation theory, then the question arises is how does that small term compare to other small terms which we have neglected, such as the fine structure terms, which were not a part of the electrostatic model. So let's talk about the fine structure terms. Let's call those H2. And let's write them like this: the sum I equals 1 to n of a radial function I'll write as C of Ri times Li dotted into Si. It's an L dot S interaction for each electron summed over the electrons with a radial dependence. I don't want to go into too much detail on what the spin orbit term looks like, so I'm not going to bother with what C sub Ri actually looks like. It's not going to be important for what we do. Also, as you know, even in hydrogen, there's other fine structure terms. There's a Darwin term and the relativistic kinetic energy, and they should be included in the fine structure as well. And I'm going to ignore them just for the sake of simplicity. So my goal here is to give you kind of an overview of what we're doing without getting into a lot of details. So if you like, reinterpret this H2 as the full fine structure terms, all of them, including all the others as well, of which this is a representative sample of spin orbit terms. In any case, the question then is, how does this H1 compare to H2? Which one is bigger and which one is smaller? The answer is it depends on the value of Z. For small values of Z, which means, essentially non-relativistic problems, then it turns out that the H2 is much less, spin orbit is much less than H1, the residual Coulomb, which is much less than H0. And so in that case, it makes sense to treat H1 as a perturbation on top of H0, and that's what we'll do. And then having done that, treat H2 as a perturbation on top of the previous result. We'll do that too. This method of this procedure, this method of proceeding is called Russell-Saunders coupling. These are the names that are attached to it, Russell-Saunders. It's also called LS coupling or LS coupling. I think I'll just call it LS because it's easier to say. On the other hand, for large Z, it turns out that the fine structure terms grow as Z squared. They grow more rapidly than the residual Coulomb. And so for large Z, the H2 is larger than or comparable to H1, depends on how big Z actually gets, which is still much less than H0. So here it makes sense to treat H2 as a perturbation on top of H0 and then treat H1 as a perturbation on top of that. If you do that, what you get is called JJ coupling. This is coupling. And if you do this, you get, it's called JJ coupling. And I won't lecture on JJ. I'm only going to lecture on LS coupling that applies for small z. And I'm going to ignore the large Z JJ coupling, but there's a, I don't know if I'll give it to you. Maybe it depends on how I'm feeling, but there actually is a homework problem that you can at least look at that involves JJ coupling in case you're curious about how that works out. All right. If you go to tables of atomic energy levels, you'll find that they're organized by LS coupling for small z, but JJ coupling for large z. You'll see, you look at uranium, you'll see it's JJ coupling. It's the way of labeling the energy levels. All right, now, okay, so that has to do then with the perturbation scheme. Well, before we get to any H2, then let's just go back to the H0 plus H1, that's to say the residual Coulomb, and let's work on that. So let's go back to the H0 plus H1. And let's remember that the H0, that our Slater determinant phi was an eigenfunction of H0 with some energy like this. Now, this Slater determinant phi, as I explained, is specified by the list of single particle quantum numbers of the orbitals that go into it. Those are central force quantum numbers. It only depends on the list. It doesn't depend on the order. So all you need to do is just say which orbitals are occupied. Or ultimately, you just give the occupation. Well, we just say which ones are occupied. That's what you do. That's what the list does for you. It doesn't matter what the order is. This is not quite exactly totally honestly right, because if I have a Slater determinant and I swap two of the orbitals, then the Slater determinant changes sign. So you can see the ordering of the orbitals in the list determines affects the sign of the Slater determinant. But if we blow off the sign, say we don't care about that because it doesn't affect expectation values, then the Slater determinant only depends on the list in question. All right. And that list in question is determined by what? It's determined by the electron configuration. And for the incomplete subshells, we have to give the magnetic quantum numbers. So this phi here, we can write this way. Another way of writing the same, something that carries the same information, is to give the electron configuration and then to give something I'll call the M set, where what the M set means, this is terminology borrowed from Beta and Jakiv. And M set, what this means is this is the ML and MS quantum numbers for incomplete subshells only. Because for complete subshells, there's only one way to assign those quantum numbers, and we don't need to specify them. This is just a way of being specific about what's contained in this Slater determinant. But the energy E0 doesn't depend on the magnetic quantum numbers. So in general, there's a degeneracy here, depending on how many different ways you can assign M sets. By the way, in most of this discussion, in the next 10 minutes, I'm going to assume the configuration is given, so I'll suppress that as well and just write this notationally as M set. But you can imagine that there's a configuration specification as well. So to give you an example, to go back to carbon again with 1s squared, 2s squared, 2p6, excuse me, 2p squared. However, the occupancies are 2, 2, and 2 out of space, 2, 2, and 6. These are the occupancies, the first row, and the second row is the capacity of the subshells. So it's the final subshell you see is incomplete. We have 2 electrons going into 6 slots. Well, the number of ways of assigning 2 electrons, and the slots, by the way, are specified by the MSETs, the magnetic quantum numbers. Well, the number of ways of assigning 2 electrons to 6 slots without regard to order is the binomial coefficient 6 choose 2. And that's equal to 15. So what that means is that it means that this Hamiltonian H0 has a ground state which is 15-fold degenerate in the case of carbon. Okay. Now, so obviously this means when we incorporate H1, we need to take into account degenerate perturbation theory. There's 15 different Slater determinants. Maybe it's a good idea to list them. Let me do that. Let me do it on a new page. Let's list them for carbon. 1, 2, 3, 4. I hope you can see this. There's 15 of them. There's some practice in doing this. Make a table here.
Professor,
Yes.
is the 6 choose 2, is that assuming like distinguishable electrons?
No, it's indistinguishable. That's the point. If I put electrons 1 and 2 in slots A and B, that's the same thing as putting electrons 2 and 1 in slot A and B.
Oh, okay, right. I'm sorry, I had it backwards.
That's why I use 6 choose 2.
Yeah, okay, thank you.
Yeah. All right, so we have 2 electrons. They have 2 magnetic quantum numbers. Let's call them ML1, ML2, MS1, and MS2. 2 magnetic quantum numbers for orbital and spin separately. And let's list them out what they can be. Well, the MLs can take on the values 1, 0, and -1, and the MS can take on values plus and minus a half. So let's suppose both the MLs are equal to +1. Then the first electron, let's give it a MS of a half. Well, the second electron has to have an MS of minus a half because by Pauli, the electron states have to be distinct. You can call it Pauli if you want. It's just a way of saying that the orbitals, the collection of orbitals have to be distinct. It's allowed to have the 2 MLs the same as long as the MSs are distinct, you see. How about, but now what about, could I have a 1/2, 1/2, 1/2 here? No, that wouldn't work, and a -1/2 wouldn't work either. What about putting minus a half first and plus a half second for the 2 electron spins? Why don't I do that? Well, the reason is because that's just a swap of the 2 states. And it's the same, as I was just saying a minute ago to the question just a moment ago, those are really the same. Because the electrons are indistinguishable, those are the same. So I can not overcount if I make sure that the magnetic quantum numbers that I'm listing are in decreasing order. This one's higher, this one's lower. So that takes care of ML1 and ML2 equals to 1, 1. This is the only assignment of MSs that are allowed for that. Let's try the next one. Let's try 1, 0. Now the 2 MLs are distinct. That means the spins can take on any of the 4 possible values allowed, but for 2 times 2. So there's 4 states with MLs 1, 0, 1, 0. Let me write them out here. And the MSs are 1/2, 1/2, 1/2, -1/2, -1/2, 1/2. And -1/2, minus a half, okay? Likewise, if I have 1, -1, there's again 4 states because 4 spin states because the L states are distinct. And I'll just write them out, 1/2, a half, 1/2, minus a half, minus a half, 1/2, and then minus a half, minus a half. Okay, that takes care of the first ML equals to 1. Let's do the next one. Let's make the first ML equals to 0 and make this one equal to 0. Why don't I make it 0 and 1? Why? Because I already did 1 and 0, that's why. And this, if I did 0 and 1, that'd just be the reverse order and be the same state. So I make it 0, 0. Now these 2 MLs are the same, so there's only one choice for the electron spins, namely 1/2 and minus a half. If I do 0, -1, there's 4 of them allowed. And it's the same story, a half, a half, a half, minus a half, minus a half, a half, and minus a half, minus a half. And then finally we get -1, which can only have a half, half minus a half, excuse me. And there you are, we did them all. and it confirms the calculation from the binomial coefficient, which was 15. We get a total of 15 states. There they are. So these are the different M sets for carbon, for the ground state of carbon. And constructing Slater determinants, 15 of them with these different M sets, gives us 15 different linearly independent multi-particle states that are all eigenstates of our H0 Hamiltonian with the same energy. By the way, I should have said this, but that Hamiltonian H0, this is called the central field approximation to the atom. You can see why it's called that. It's because the potentials have been averaged in order to make them central force fields. This is a cruder approximation than the electrostatic model. It gives worse energies than that, but it's easier to solve. And that's in fact what we're doing now. We're solving this a fully multi-particle problem, and then we're going to use perturbation theory. All right, anyway, this is the central field approximation. The central field approximation has more symmetry than the electrostatic model. It's a cruder model. And in particular, it commutes with the individual orbital angular momentum operators L vector sub I because it's a sum of single particle Hamiltonians, whereas the real electrostatic model does not. All right, anyway, that's a central field approximation. All right, so then to go back then, the this H0, phi 0, or let me write this way, H0 onto this M set is equal to the E0 times the same M set. This is for the ground state of our H0 Hamiltonian. This is, in the case of carbon, is 15-fold degenerate because of the 15 possible M sets. Now then, to get the energy shifts from H1 using degenerate perturbation theory, you just take these degenerate eigenstates of the unperturbed Hamiltonian, sandwich around them in H1, and I better put a prime on one side because we're going to get a matrix here. This would give us a 15 by 15 dimensional matrix, and its eigenvalues would give us the energy shifts. Well, it isn't the philosophy in this course to diagonalize 15 by 15 matrices. As you know, we try to get by without diagonalizing anything. And the way we do that is by choosing a clever basis. So what basis do we want to choose? It's not going to be the M-set basis, hint, hint. What's a different basis? What will it be? The answer is that it ought to be the basis, which is the basis of the good quantum numbers of the Hamiltonian. We talked about what they were already. That's the L, M sub L, S, and M sub S, and M sub S. And I don't really need to talk about parity because that depends only on the configuration, and so it's constant. This is all with respect to a single configuration. So for the carbon case, the parity is +1, and we don't need to worry about it. But these four quantum numbers, it would be nice to have them, to use them as to create a good basis. So a good basis is not the M-set basis, but it's an eigenbasis of L squared LZ. Let me write it this way: L squared S squared LZ and S sub Z with quantum numbers L, S, ML, and MS. And what are these equal to? These are equal to a linear combination over M sets of some coefficients multiplying onto the M sets. They're linear combinations of these 15 Slater determinants, which are eigenfunctions of those operators. These coefficients, as you can see, are sort of like Clebsch-Gordon coefficients. The individual M sets are eigenfunctions of individual L sub i's and S sub i's of the individual electrons. These are combined together to give you eigenstates of the total L squared and total LZ, total S squared and total SC. So in that sense, these are like Clebsch-Gordon coefficients. They're computed in a similar way, actually. All right. However, if we've done this, then the energy shifts delta E are given by what? They're given by the LS, ML, and MS sandwiched around H1, which I'll remind you is the residual Coulomb Hamiltonian, like so. And we don't need primes on any of this, on either side, because all of the operators in question commute with H1. Now, the energy shifts delta E, what are they going to depend on? They're not going to depend on the magnetic quantum numbers. They're going to depend on L and S. So what we're going to end up with is in first order perturbation theory, is a collection of states that depend on the LS quantum numbers. This is going to be added to the E0, of course, but the E0 is the same for all 15 states. But what we're going to get for the energy levels when we do this perturbation calculation is levels in which that E0 has been split, and the new levels are labeled by their L and S values. These are called multiplets, and in fact, these are the identifying labels of the low-lying energy levels of atoms. So you need to use them in order to talk about those energy levels. Okay, so I'm essentially done for tonight. The plan for next lecture is to show you in enough detail to understand the idea of what we're really doing, how we carry out this perturbation expansion. The initial goal is to find out which L and S values occur in this sum, or let's say in the ground eigenspace of our H0 central field Hamiltonian, central field approximation Hamiltonian, which L and S values occur in that ground state. This is a generalization of the problem of finding which total J's occur when you combine J1 plus J2. Now there's multiple electrons have to be combined. It has to be antisymmetric and so on, but it's going to give some total S and some total L values. We need to know what they are. So that'll be our first task in the next lecture next Tuesday night. All right, so that's all for tonight for the substance. Are there any questions?
The coefficients here, you said, so they are the Clebsch-Gordon coefficients? They're derivable from those, or are they?
They're like Clebsch-Gordon coefficients. I mean, the usual Clebsch-Gordon coefficients arise when you couple two angular momenta to create a third.
Yeah, so we're coupling a whole bunch.
We're coupling a whole bunch of them. We have two different kinds of angular momenta, orbital and spin. They have to be coupled separately to give a total S, total L and total S. We have to respect the antisymmetry of the wave function. And there's in general more than two electrons. So all of that makes it more complicated than the usual problem, but the basic idea is very similar, and these coefficients are really very much like Clebsch-Gordon coefficients. By the way, don't be intimidated by it. It's not that hard to actually determine these coefficients. It's just you just use raising and lowering operators. You can get them without much trouble.
Cool, thanks.
Any other questions?
If you couple those magnetic quantum numbers pairwise, like say a bunch of times, can you just use the Clebsch-Gordon coefficients?
Yeah, chains of Clebsch-Gordon coefficients. Probably if you're clever. Yeah, see, the problem with using chains of Clebsch-Gordon coefficients when you're trying to couple more than one angular momentum, the problem with that is that there's more than one way to do it. You know, if you have three angular momentum, you know, J1, J2, and J3, we can couple J1 and 2 first and then add J3 to that. Or we can add J1 and J3 first and then add J2. And this gives you different expressions. And you have intermediate quantum numbers. So anyway, yes, you can do it, but believe me, it's best avoided if possible. In this context, in this problem, we don't need to do that.
Okay, thank you.
But let me just say that if you get into coupling, if you ever do the real theory in this, you'll have to worry about coupling multiple angular momenta in different orders, and this leads to the subject of the Wigner 6J symbols and things of that sort. It's an arcane topic that people are interested in. Okay, any other questions?
I had a question. I was just wondering if you could touch back on you were talking about how electrons are not actually like filling the orbitals themselves or the subshells themselves. You were talking about how they're kind of in every subshell, and I was just, I don't know.
Well, you can say which subshells are filled because those are the wave functions that appear in the Slater determinant. You just can't say which electron is filling it.
Oh, okay.
Because all the electrons are permuted amongst all the shells. all
Okay.
the orbitals.
Okay, I thought I was fundamentally not understanding electrons there for a little
Yeah,
bit.
thank you for clarifying that.
Okay, cool. Thank you.
Anybody that's got any confusion question like that, please ask, because I'm glad to answer it, and I'd rather have it be straightened out instead of going on and have things be murky. Any other questions?
Actually, a logistics question. Next week, are we going to be on Zoom?
Yes, we're going to continue lectures on Zoom. However, I'm going to start doing office hours in person. I sent out an email about that. Not tomorrow because I didn't get a room in time, but I'll start next week.
Yeah, okay.
Yeah, so take a look at that email I sent out today.
All
I
right.
hope,
Thank you.
everybody got it. Any other questions? All right, if that's the case, then I shall stop screen share. And I shall stop recording.